As many of us are aware, a central theme of the past FAT MLs have been fair classification, by which I mean the development of methods to fairly predict categories. In criminal risk assessment, the categories might be something like future recidivist, future non-recidivist. In other settings like lending, the categories might be creditworthy or non-creditworthy people. So this session continues on that tradition by focusing on classification, but this time with a multidisciplinary spin. So our first two talks give technical depth into the creation of fair categories. The second is an empirical assessment of the fairness of a scheme for categorization. And our last talk is from the field, I had it written down as political theory, but it turns out it's philosophy, and I've never attended a talk in either of those, so I'm absolutely delighted to get to hear one today. And because of this, in my mind, this session really embodies sort of the spirit of Fat Star and bringing together scholars from a wide variety of disciplines to talk about something relevant to fairness. And I think it's also worth mentioning that in this session, we have both of our best paper awards, so I just wanted to very quickly acknowledge that as well. The Cost of Fairness in Binary Classification, which we're about to hear about, won the award for the best technical contribution. And a case study of algorithm-assisted decision-making in child maltreatment hotline screening decisions, which is our third talk, won the award for the best technical and interdisciplinary contribution. So since the content's obviously great, I'm going to quickly just get started, so thanks.
Thank you. So this is indeed joint work with my colleague, Aditya Menon, who unfortunately couldn't make it here today. So I'm looking at the problem of learning binary classifiers. It's perhaps the simplest machine learning problem. You get some measurements, say, of a person, a feature vector, a set of measurements about a person, and your job is to predict something about them. Will they be a good student in college based on the information that you've got? There's a very clear definition of this problem, and there's a clear performance goal, which is the maximum accuracy. Learning fair binary classifiers, as is formulated in the field, is to do the same thing with a constraint. As well as being able to predict the thing that you're interested in, you want to take account of some balance across a protected attribute. So in the cartoon, it's clearly the sex of the applicant. So there's some notion of having a fair balance, as well as having a highly accurate solution. And in practice, I mean, you can never achieve perfection in anything. It's the engineer's motto. So you will settle for a sufficient degree of fairness, and so you want a knob that adjusts that. This begs a very obvious question, which is, what is the cost of doing that? There is going to be some trade-off. We already know that because the base problem, I said there is some measure which is the best that you can do, and now I'm imposing a constraint. So that's what the talk is about. In the paper is quite mathematical. Half of the slides have some equations on, to be fair to the mathematicians in the audience, and the other half don't. I will endeavour to explain the intuition behind it and focusing on, the implications of it. So how do mathematicians think about binary classification? You have these two distributions, and they might vary over time, or vary according to different parameters. The blue might be the conditional distribution for the girls. The yellow might be the conditional distribution for boys. You might be trying to, sorry, that's a bad example. You've just got two classes and you're trying to discriminate between them, right, on the basis of the measurements you've got. Here, the feature vector is just one-dimensional. And what is a classifier mathematically? It's just that red line, right? The red line is the thing that separates them. So you say everything to the left is in class A and everything to the right is in class B. Now, if the distributions were actually as they are in that picture, then you will make errors. And depending upon where you draw the line, the errors will vary. So you'll see here to the left of the red line, there's a lot of yellow mass. That's going to be, say, a false negative. We predict that it's negative, but it shouldn't have been. The little blue area to the right, that will be a false positive. Moving this line around is fiddling with what's called the loss function. It's the way you measure how well you're doing. So I've already said that. So you see the two tails. So these are the error measures that you've got. Now, that's the base problem. What about when you introduce the notion of fairness? So fairness is an additional ingredient. There's something else that you're measuring. right? And in the simplest problem that we look at, that too is binary. It might be race, black versus white, sex, male versus female. And that's separate distributions, and the problem we're looking at is design a classifier to solve the basic problem and then check its performance on the protected attribute, right? So mathematically you can set that up. And it's tricky because these sets of distributions are kind of independent, right? So you could have the protected attribute being different. So how do you go about solving that? So there is a formal framework in which you can pose these questions, and it is quite old. Abraham Wald formalized it, and one of the crucial things is that there is this notion of a loss function. So the loss function, so in the economist's language, it's a utility. It's an outcome contingent utility. And the whole point is that you have some intuition of what matters to you, you abstract it and turn it into a mathematical function. The thing that you actually try to optimize is the average of that, averaged over the population. And so we now have an unambiguous definition of what optimal means. By definition, the optimal hypothesis achieves the minimal risk. In the toy example, the optimal is just the threshold at the red line. Now, where you choose the red line is the crucial thing. We've only got one knob, so there is a way of figuring that out. In general, that's a complicated story. But and the other thing to keep in mind is that the minimal risk in general is not zero, right? That's another way of thinking of that is that there's always noise. You measure this stuff, but that doesn't allow you to predict everything perfectly. So the key point, right, so this is classical stuff, you can formally write down a formula for the optimal hypothesis. And this is it. It doesn't look too scary. The ingredients there are a distribution. It's a conditional distribution. It's a mathematical abstraction of the data. Right? It's a theoretical construct, though. It's not the data, it's an abstraction. We never actually have access to this distribution, but for theoretical analysis, we'll suppose that we do. What the formula says is you take this conditional distribution, you ask when is it above a certain value, C is a design parameter, and if that condition in the funny square brackets is true, output 1, meaning yes, otherwise output 0. So that is a complete formula for the Bayes optimal classifier, as it's called, for a classification problem. That's in textbooks and that's all fine and good. Now, why bother with this theoretically optimal hypothesis? It's unrealistic because it assumes infinite data, infinite computation. I'm ignoring all of those issues. So why is this even worthwhile at all? Well, if you can demonstrate a problem when using the optimal thing to do, then in practice, life is even harder still. More significantly, you can actually reason theoretically and legitimately make comparisons, which is much more fraught if you're using algorithms, because then it depends upon which algorithm. So if we're doing the optimal thing, then life is good. How do you formalize fairness in this setting? Now, this is not new. This is standard in the fair machine learning literature. So the key idea is that you have a protected attribute, that might be your race, that's the Y bar. You're trying to predict a particular thing, the Y hat, whether the person will succeed in college, and you can define these formulas. The exact form of them doesn't matter. The details are in the paper. They've got these names, mean difference score and disparate impact factor. Really all you need to take away is that it is a formula, it's unambiguous, and what does the formula depend upon? It depends upon these joint distributions. The distributions model the data, right? So you've got the abstraction of the distribution, you have some formula, they're not arbitrary, they actually do make sense, and with that you can measure the degree of fairness, which is capturing the degree to which you will be potentially harming a protected class or something. So, how did we get the result that I will present shortly in the paper? So the crucial thing, the crucial helper result that we showed was that these fairness measures, DI and MD, they can be expressed in terms of something else that we've already got a really good handle on, and that's this risk. These risks for cost-sensitive classification, that's what the CS stands for. Again, the exact form of this result doesn't matter. What it says, though, is that given a particular fairness measure, if you want it to achieve a certain value, that is equivalent to, that's the double-headed arrow means that if and only if, this thing on the right holds true. So instead of saying I need to get this fairness measure to be at a certain value, I now have to get this risk to be at a certain value. And that's nice because we know how to manage risks. We know how to manipulate them, and we can do proof theorems about them. The paper, we have this result for both the DI and the MD. There's technical subtleties about exactly how all of that works, but the stuff in green is the key point, right? So we've started framing the problem in the standard way with the fairness measures, but now we've transformed it into machinery that we can make progress with. And so the way we think about, so how do we analyze these problems? So the normal way that you solve a machine learning problem is, so we're going up another level of abstraction here, you have some risk measure, right? And it depends, there's lots of different choices of R. You have this distribution D. All of those distributions I was writing up before, I'm packing into that symbol, and you have a hypothesis F. F is the thing that you get to choose, where to draw the decision boundary. Now there's zillions of different Fs that you could choose. What this formula says is, this is the thing that you'd really like to do. Minimize over all possible choices the risk on the data that you've got. What we show in the paper is that the fairness-aware setting can be formalized in an analogous fashion where you just augment the original problem with this additional term. So you see the equation in the middle, the thing on the left is the same, but now we've subtracted. And the fact that it's a subtraction is a bit odd to get your head around at first, but it is indeed a subtraction of a different risk with respect to D bar. D bar is the distribution that takes account of the protected attributes. D, you have the feature vector, the x's, and the thing that you want. D bar, you have the feature vector, same feature vector, but Y bar, the protected attribute. They're both probability distributions over a joint space, but they're different ones. But we use the same notion of a risk measure for both of them. So this is beautiful. If you're a mathematician, you get this nice, elegant formula, and we can make further progress on this. Now, we don't do it for general R, we do it for these cost-sensitive risks. They're particularly nice because they're easy to understand, and crucially, they're easy to manipulate mathematically. So this is really the punchline of the whole paper, really. This is a formula. It might look hard to parse if you haven't read these things before, but if you ignore the stuff in red, it was the first formula that you saw. If you ignore the stuff in red, or equivalently set lambda to 0, lambda is a knob. Greater than 0, it's a design parameter. Effectively, cranking lambda up is imposing a greater degree of fairness. What this shows you is what the optimal classifier looks like for the more complicated problem of do as well as possible given a targeted degree of fairness. And now it's got a nice interpretation. So here's all of the different ingredients. I've told you the stuff in blue. The stuff in red, the way you think about it is it's an instance-dependent threshold. Previously, you just took this joint distribution over the data that you're interested in, and you just thresholded at a certain point. Now, you vary that threshold according to the x, and the exact way you vary it depends upon the conditional distribution of the protected attribute conditioned on that x. Now, it takes you a little while to get your head around the implications of this, but the crucial point, the takeaway message, is that you can actually solve it. Now, a priori, it's not obvious that you can do this. The vast majority of machine learning problems in the world, you can pose them as I've done, but you can't write down a formula like this, right? But remember, I am cheating. I am presuming that I have access to the full joint distribution, which in general you don't. In the case where you actually use the sensitive feature as an input, the solution actually simplifies a little bit. That's spelled out in the paper. Now, since we can do that optimal thing, we can actually work out this fairness frontier, right? So the title of the paper is The Cost of Fairness. So you can ask the question, as I increase the fairness, does my error go up, and how much? And we're interested in the best possible. It's not just any old algorithm, it's the best possible algorithm. Infinite data, infinite computation. You can formalize this, it just becomes a constrained optimization problem for the people that can parse that quickly, but that's not essential. The crucial point is, since we can compute the Bayes optimal hypothesis, then we can compute this frontier. precisely, exactly, with no approximation. And you can get a nice formula. Again, if you like these things, this is beautiful, because it gives you some insight into what's going on. What this is the complete expression for the frontier. The qualitative features to look at are that it is effectively measuring a degree of disagreement, a measure of disagreement between the y, the thing that you're trying to predict, and the y bar. Imagine it was the case that you're trying to predict whether people will do well in college. And suppose it was the case that only girls could do well in college. Every girl did fabulously and every boy did terribly, right? It's an extreme example. In that case, you've got no wriggle room. Both things are completely aligned. This is measuring the degree of alignment, but it's not just any degree of alignment, it's the right degree of alignment for the problem as we posed it. So again, the takeaway point is you can actually compute this thing analytically, right? Which is interesting. And that suggests that you could estimate it empirically. We haven't done that yet. There's some technical complications to do so, but there's no reason to believe that it can't be done. The only question is how well can you do it? So to wrap up, I want to just finish in the last couple of slides on interpretations and implications. So you could frame what we're doing as finding the intrinsic limits to performance of any algorithm solving these fairness problems as posed. And remember, I just looked at a couple of fairness measures. And I think that this is a great baseline thing that you should try and do for as many things as possible. And it's analogous to a lot of scientific work that's been done in the past. It's the same relationship as thermodynamics has to the theory of heat engines, or Shannon's information theory and its relationship to real communication systems, right? It's the limits of the possible. So that's nice. Philosophically, there's some interesting things about when you look at it this way. It's entirely probabilistic, so for people who know this literature, it's much more akin to John Hassani's setup of the fairness problem than John Rawls'. It presupposes the unambiguous existence of the groups defining the protected attributes, right? Now, male, female, that might be obvious, but it's not without contention. In other cases, there is contention, and so an obvious extension here is to degree with partial membership, right? So with probability 0.8, you're in the protected attribute. So there's, that's opening line of future work. And just in passing, can I mention, dealing with groups in this fashion is not new to statistics, right? It's called the ecological fallacy for the past 50 years. The paper shows that you should focus on trade-offs, not solutions. This is standard for engineers. I think even more interestingly is it brings to light this idea of the partial truth of stereotypes. So that's the phrase that the social psychologists use, and they try and quantify this sort of thing. Suppose it was the case that only girls could do very well in college, we'd all have a stereotype. Every boy that you would meet, you would immediately think that they're going to be terrible in college. And if it was true, right, what I presupposed, you would be exactly correct. But the world is much more noisy than that. So I think this gives you some insight into how you might go about trying to estimate those degrees of partial truth. And the final point, which I think is also quite interesting at a philosophical level, is that we've conjoined two things which some folks, I know, believe you should never conjoin, right? You're taking something like fairness, which is about, I don't know, fundamental human rights and dignity and what have you, and you're comparing it with money, right? Is that what you're really doing? Yeah, yes, that is what we're really doing. Why? Because it will be done no matter what. Even if you don't like it, it is going to happen. So you might as well work out what the trade-off's going to be. There is an interesting sidelight here that some social psychologists have looked at such things. So Philip Tetlock and Alan Fisk wrote this paper on taboo trade-offs, where you compare something within one domain of sociality or one sphere of justice with another, and that can often get people worked up. So to conclude, we studied two basic questions. What is the optimal fairness accuracy trade-off, and how do you achieve the optimal trade-off? And we solved that problem completely for specific cases with these cost-sensitive measures. And we found that the optimal classifier, you just adaptively change the threshold. A priori, it was not obvious that the solution would be so simple and elegant. So it's nice that it is, and it offers new opportunities. And the trade-off, we've got an explicit formula for the correct measure of alignment between the target and the sensitive class probabilities. So that's the thing that is kind of capturing how hard this problem fundamentally is. And there's a few to-dos. I've mentioned the uncertain labels. There's obvious extensions to multiple protected attributes and multiple labels. And, you know, more speculatively, I suspect that these more formal mathematical tools may eventually be able to contribute something back to ethics. Thank you.
Other questions? Okay. Just to expand on that last bullet, in fact, I think if you treat fairness as the mutual information between the protected class and the score, and then the thing you're trying to optimize is the mutual information between the score and the label you're trying to predict, I think all of this is the information bottleneck.
It's related to that, and so when you talk about the mutual information, that presupposes certain ways of measuring the information. There's no single measure of information. You can re-express what I had up here in terms of measures of information, but it's not the Kullback-Leibler divergence.
No, I mean the Shannon mutual information.
Sorry?
I just mean the Shannon mutual information.
No, it's not Shannon information,
Okay.
right?
Okay.
Shannon information is the right thing to use for certain things, but it's not the only thing. There's a non-countable infinity of information measures.
Okay. I look forward to hearing more.
Yep. Okay.